Hello, I'm Jin Wang from Tsinghua University. I'm glad to present our work on combining NeRF and inverse rendering. I'm grateful to collaborate with Ruihan, Feng, Cheng, and Shuang in this work. Physics-based inverse rendering can reconstruct shape, material, and lighting conditions from 2D images, which is useful in 3D reconstruction and scene digitization. It typically optimizes scene parameters to minimize the difference between captured images and renderings. To accurately simulate light transport, an accurate scene model is crucial. Therefore, in this work, we focus on a more accurate lighting representation. Given object-centric captured images, inverse rendering tends to model the object in terms of shape and material, while approximating the rest of the scene as a distant environment. The environment map is popular because it is a default choice in forward rendering to model environment lighting. It is also widely implemented in physics-based renderers like PBRT and Mizpa 3. Inverse rendering solutions tend to follow the tradition of forward rendering. However, using the environment map can lead to inaccurate inverse rendering results. In these cases, we can see artifacts around inaccurate shadows and bumpy geometry around glossy reflections. So what is the cause of the problem? It turns out to be the distant lighting assumption of the environment map. When using environment maps, the lighting distribution is assumed to be spatially invariant when excluding visibility. When the shading point moves, the lighting of the environment map does not change. However, the lighting in the actual captured scene is not distant. It shows strong parallax effects like the one below. Therefore, we need a lighting representation that can model spatially varying incoming radiance. Our work finds that the neural radiance field is suitable to represent the spatially varying lighting. NeRF essentially models the 3D radiance field, which extends the 2D radiance field modeled by the environment map. As an emissive volumetric light source, NeRF is a naturally perfect candidate for lighting. It is originally used for novel view synthesis, but we show that it can be extended to light modeling, because moving the shading point is just like moving the viewpoint. Recent advances in NeRF also make it more suitable for light modeling. Unbounded scene enables modeling the surrounding environment. Training acceleration makes the computational cost more manageable. HDR radiance is also crucial, as light sources are significantly brighter than ordinary objects. Therefore, in this work, we propose the first inverse rendering pipeline that renders surfaces under NeRF-based lighting. Our method jointly reconstructs shape, material, and NeRF lighting from the captured images. To integrate NeRF into physics-based inverse rendering, we devised an emitter important sampling approach for NeRF to reduce the rendering variance. We capture both real and synthetic datasets featuring long-distance lighting for evaluation. By using our NeRF lighting in inverse rendering, we can see that it leads to better reconstruction under shadows and reflections. We also test our method on real captured data and find that it leads to higher quality relighting and does not suffer from these artifacts in the baseline. Our method combines surface rendering and NeRF. Surface rendering assumes a vacuum between the surfaces and obeys the rendering equation. NeRF assumes the scene is filled with emissive volumetric densities and is modeled by the volume rendering equation. To render the hybrid scene consisting of both, we derive the rendering equation considering both surfaces and NeRF. Please refer to our paper for details. Based on a bounding box of the object, we divide the scene into two regions. In the internal region, the object is represented by surface and material. In the external region, the surrounding is represented by the NeRF-based environmental lighting. We perform path tracing within the bounding box, and query NeRF when the ray goes out of the bounding box. Physics-based rendering requires multicolor sampling. However, BSDF sampling only will render a lot of noise under a NeRF light source, so we need an emitter important sampling method for NeRF. Our base idea is to approximate bright regions of NeRF using a Gaussian mixture model. First, we sample random rays to construct a NeRF point cloud. We only retain the bright part of the point cloud inspired by MIS compensation, and cluster the point cloud to build a Gaussian mixture model. During important sampling, The Gaussian mixtures are projected to VMF lobes at a shading point. The sample direction is combined with BSDF sampling by multiple impedance sampling. To show the effect of emitter impedance sampling, we compare the rendered gradient images with respect to the vertical translation of the objects. When using high samples per pixel, our rendered gradient images match the finite difference reference. When using the same SPP, our rendered gradient images have much lower variance than pure BSDF sampling. We build NeRF evaluation and impedance sampling as an emitter plugin in NeSPA3. However, NeSPA3 cannot call neural networks within the megakernel. Therefore, we split one rendering operation into two megakernels. Specifically, the first kernel generates rays to cover the NeRF lighting, and the second kernel gathers enough radiance to compute the pixel color. The neural network operations of NeRF evaluation take place between the megakernels. We use SDF and material voxel grids to represent the object, and progressively upscale the voxel grids during optimization. We enable the NeRF to model HDR radiance to be suitable for light modeling, and apply contraction to handle unbounded scenes. To aid the convergence, we design a multi-stage optimization process. By first performing ordinary NeRF training and use the NeRF density to initialize the SDF shape. Then, we jointly optimize shape, material, and NeRF lighting. We obtain the final shape by matching cubes and texture unwarping. To thoroughly test inverse rendering on scenes where the light is not infinitely distant, we capture a dataset featuring non-distant light sources. Because a single light condition is ambiguous, we put the object on a turntable, rotate the object, and obtain multiple lighting conditions. We utilize a DSLR camera with bracketed exposure to capture HDR images. We employ a laser scan to obtain the reference shape used for quantitative evaluation. In this example, we show a real capture scene featuring shelf shadows. When the shading point moves, our method can model the spatially varying lighting and its impedance distribution, while the environment map is not changing. We can synthesize novel views by rendering the hybrid scene of surfaces in the middle and NeRF in the surrounding. During relighting, we can observe that the attached shadows are baked into the baseline on the right, causing artifacts. Our method on the left generates higher quality relighting results. In this example, we show a synthetic teapot scene featuring glossy reflections. In the original lighting, the rendered highlights in the baseline on the right do not match the actual scene. In contrast, our method can more closely match the glossy highlights. The relighting results on the right reveals that the baseline contains inaccurate material parameters and geometry bumps. Our method on the left can render more accurate highlights during relighting. For limitation, the main drawback of using a NeRF lighting is the increased computational cost. Accelerating NeRF, however, is an active research topic and can improve our method. Some increases NeRF evaluation speed, and others reduce the samples per pixel. Also, the current emitter impedance sampling method does not consider highly directionally dependent illumination. More advanced guiding techniques may solve the problem. To conclude, we believe that NeRFs can be used beyond view synthesis in physics-based pipeline. Our code is available at the project page. Thanks for your attention.